Okay, so now that we've fully formulated our theory of special relativity, we've introduced space-time, been introduced to the concept of observers and reference frames, and we started talking about how these reference frames are related by Lorentz transformations. We can now start putting all of this together and start talking about relativistic dynamics. So we're going to be looking to realise all of the nice things that we're used to dealing with in classical mechanics, like forces and momentum and energy and all that stuff. We want to see how these now translate into the relativistic setting. So let's just remind ourselves of what we have so far. We've formalised our space-time, or rather an observer that views our space-time. And they simply construct whatever coordinates they're going to use to measure that space-time. And now the only real dynamical quantity which we've begun talking about, well, first of all, we can consider the world line of an observer that travels through this reference frame. And we've seen how by doing some kind of similar analysis on this curve, we can consider its tangent velocity, which is now a four velocity or a space-time velocity. And this is really only the kind of dynamical quantity which we've encountered so far, this four velocity. And we've seen that it is composed of a spatial velocity or coordinate velocity piece, and then a kind of time, or rather a coordinate time velocity piece, which is somehow related to our Lorentz factor gamma. And so obviously this four velocity is going to factor in quite heavily when we start talking about dynamics, as it is quite clearly related to the dynamics of this moving observer. But now, as well as just simply talking about world lines and reference frames, we know that we also have Lorentz transformations, which we can use to transform between these two observers. And we've seen how these Lorentz transformations mean that we can no longer use these space and time coordinates to essentially to describe anything physically meaningful, because they're only physically meaningful for the observer who sits at the origin of that frame. All other observers are going to measure different, potentially different values for those quantities. And so when we're now wanting to start talking about dynamics, or how quantities in space-time change and how they're related to each other. But now when we want to start talking and building theories of dynamics, we're going to need to now step away from talking about coordinate dependent quantities and now start looking at invariant quantities, or so-called Lorentz invariant quantities, which are going to be invariant regardless of the coordinates that you're using. And so as we've started to see, we can build such invariant quantities, or Lorentz invariant quantities, to give them their relativistic name. We've seen how we can consider Lorentz invariant quantities, and one of the main ways that we would construct a Lorentz invariant quantity is using the metric. And so we saw that this metric, or the line element, is going to be invariant for all frames. So whatever the value ds squared as measured by one frame is, it always has to be measured to have the same value by any other frame. And we saw how this leads us to the notion of proper time, the time at which you would experience if you were living just simply within your own frame and travelling along a straight world line. And so it's this proper time, or rather now we can understand proper time as simply just being the length of your world line in your own frame. And because this is an invariant, all other observers can measure this length. They can all see how much time your clock thinks has elapsed in its own frame. And so this proper time is now a good quantity to use to start formulating our physical theories using, because it's available for all observers regardless of the reference frame that they're in. And so we write down our world lines as parameterized functions of this proper time. And of course the forward velocity is then the parameter or the tangent vector to this world line. So I mentioned forward velocity is going to have a lot to do now when we start talking about dynamics, and it's going to be the route we take into dynamics is going to be starting with forward velocity. So let's just remember how we defined the forward velocity. We said that this forward velocity, which I'm giving the name u, is simply now just the parameter derivative of this world line with respect to our parameter, which is the proper time. And now, when we realise our world line is a parameterized function, we're just essentially writing down a vector that gives a position vector that gives the coordinates as a function of this parameter tau. And so when we take this derivative, we simply arrive at the following object. This is now just simply the parameter derivative with respect to tau. And we said that this thing, this dt by d tau, is going to be the Lorentz factor. We've now seen a lot more about what this Lorentz factor does and how it really controls all of our relativistic physical effects. And then we can also just rewrite using the chain rule this dx by d tau component in terms of the dx by dt, which is the coordinate velocity v, essentially how fast you're measured to be moving in the A-frame coordinates. And then we also had to include the gamma factor from the chain rule. So this is our forward velocity. We've seen this before, and I'll just now rewrite it in its simplest form that we're going to be using. So the time component is just this c gamma, and then the space component is the coordinate velocity, also times gamma. So now that we've identified or understood our forward velocity, we can use it in defining some other more interesting quantities. So just immediately from the forward velocity, we could just immediately then ask, well, what's the derivative of forward velocity going to be? It's something like a forward acceleration now. Just simply understood as either the second derivative of the world line or the first derivative of the forward velocity. So just to quickly verify that this A forward acceleration is a good quantity, or rather does it transform nicely under our Lorentz transformations. Now I'll just really quickly write this without any indices or anything. So we basically just need to have that the forward acceleration, when we Lorentz transform it, just turns into some other transformed forward acceleration. And so we have to now look at this expression and see if that's true. Well, when we Lorentz transform, we're going to be affecting this u. And so what we're going to realise is that we're going to have the Lorentz transform of u. And now since this lambda is just a constant matrix, it's not affected by tau, this is just lambda and then times du by d tau, which then is of course just lambda times a. And then this thing over here would be a hat. Okay, so that's fine. This forward acceleration is a good space-time object. Okay, so now I just want to go through and note something that's quite interesting about this forward acceleration, is that we can actually calculate that it's going to be orthogonal, or now Minkowski orthogonal, to this forward velocity vector u. And by Minkowski orthogonal, I of course just mean that the inner product between the u and the a forward vectors is going to be 0. So essentially I'm just trying to show that when we contract, we'll take the inner product of the forward velocity vector with now the forward acceleration vector, we're going to find that this is always 0. So to do this, I'm actually going to start in a slightly different place. I'm going to start with the normalization condition we derived for this forward acceleration, which, if you remember, we saw worked out to be, if we take the inner product of this full velocity with itself, i.e. just contract it twice against the metric. This always has a constant value of minus c squared, which first of all tells us that this full velocity vector is time-like, because this value is negative, so the full velocity always has to point within the forward light cone, and it always has a constant fixed value, and so the space-time length of this vector is always fixed, but it's just now how that space-time length is distributed over space and time components, and we can see that since this is always fixed, your space component is essentially also constrained, and we saw that this constraint essentially constrains the value v to always be less than c. So we've derived this before. This was just our normalization condition for the full velocity, but now let's just do something that might feel a little bit strange, but let's just take a tau derivative of this expression. So I'm just going to take the derivative with respect to tau. Of course, another constant, it's just going to give us 0. And now I'm going to have to use the product rule on these three terms. Obviously the derivative of this eta is always going to give 0. And so I just essentially need to calculate what is the tau derivative on this product here. And so just using the product rule, I'm going to get now 2 times the derivative of one of these u's with respect to tau times the other u. And then of course with the metric still unaffected by the derivative. And the 2 here just because I'm using the product rule, take the derivative of this first one and then have to add to it the derivative of this second one. Okay, so this is now our expression. We can identify that this is going to be the full acceleration. But now really what we've basically arrived at is what I wrote down initially, if you like, the inner product between the acceleration and the full velocity vector. We've seen that we just do this by contracting them against the metric, and so I can of course just cancel the 2, and so I find that well, now this is essentially stating that the A and U vectors are orthogonal, or now Minkowski orthogonal, i.e. they have 0 Minkowski in a product. So this is just something to always keep in your mind, that the full velocity is going to be orthogonal to the full acceleration.